Hi there. The purpose of this video is to show how we can develop a mathematical formula from a given problem. So the problem in this case is a ball is thrown straight up in the air with initial velocity 14 meters a second. It starts from a height 3 meters above ground, and gravity works against the initial velocity, pulling it down with acceleration 9.81 meters per second. What we want to do is to derive a formula for the height of the ball at any time t. We want to know the time when the ball will hit the ground, and we want to know at what time will we reach maximum height. And we'll do this both graphically and analytically through Excel. So if we go down, the problem here is we need to decipher the words here. So what we want to do is we're going to let height h be a formula from time t squared, t to the power of 1, t to the power of 2, and so on. We know the starting height at t equals 0 is 3. So this constant a here must be 3, because any number to the power of 0 is 1. So we know this part of the formula has to be the constant 3, because that's when we start at height. We know the upward velocity is 14. Velocity is the rate of change of displacement. In this case, it's height, as in height upwards. So that equals the height divided by the time. If we rearrange this formula, we get the height going up, if there was no gravity, as velocity times time, which is, in our case, is 14t, because it's velocity 14 meters per second. What we also need to do is to work out the effect of acceleration downwards. Acceleration is the rate of change of velocity, which in turn is the rate of change of displacement, in this case height. So acceleration equals the height divided by time, and time again, height divided by t squared. If we rearrange this formula here, we get the height going down as acceleration times t squared, which is minus 9.81 t squared. So we've now finalized our formula for height at any time t is minus 9.81 t squared plus 14t plus 3. We can see we've got a squared effect here, so this formula is non-linear. It is not straight line, and we will see the shape through Excel. We have a quadratic formula here. For height equal to 0, we can use the quadratic solution minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. A is the constant minus 9.81, b is 14, c is 3. If we plug in these numbers and jump through the computation, we get two possible values for t. The negative one is nonsensical. The valid one is time equals 1.6163 seconds, and we'll confirm that graphically through Excel. The last part of the challenge was at what time will the ball reach maximum height? So we throw the ball up in the air, it goes upwards, and at some point gravity overcomes the upward effect and it reaches maximum height and drops straight back down to the ground. So when the rate of change is height is 0, we know we've got maximum height. So what we want to do with an analytical calculus, we want the rate of change of this initial formula against time, the rate of change of h against time. So the rules of calculus, that exponent comes in front and you subtract 1 from the exponent. So we end up for the rate of change formula is 2 times minus 9.81t plus 14. And we want to solve that for equal to 0. And if we plug through, rearrange the formula and plug, and we do the computation, we end up with a time of 0.713 seconds. And at that particular time, we get a maximum height of 7.995 meters. Now, what we want to do now is show through Excel how we can prove that those numbers are valid. In this left-hand column in Excel, we've got time, and in this case we control the resolution, how the step change in time going through the computation line by line. I've chosen 0.01, and then all you have to do is just double click on that, and then it'll increment the resolution by 0.01 steps. What we've got in this column here is we've got a formula for the height. So what we want to do is we plug in these constants in these cells and then pull them over to these cells using the dollar so that we bring in these fixed cells, but we've got the formula executed for different times of t, stepping through line by line. We can see if we've got the formula correct here, we must start at 3 meters above ground. And as we throw the ball up in the air, we can see the height is increasing. If we just simply go down this column, we can actually just do a visual and actually see what maximum value we get down here. We can actually see here that the maximum value we get here is 7.99477, and then it starts to drop off again. So between 0.71 and 0.72, we have time. We know we have maximum height. The other thing we're asked to do is what time we hit the ground. So again, if we look through that column and we've got our formula correct, we get down to time 1.61, we're just above the ground. We get down to time 1.62, we're going negative ground. So we've obviously hit the ground between time 1.61 and 1.62. And if we plug in our formulas here, then we can plug in the formulas being shown on the slides. We come out with the time 1.616 seconds, we hit the ground. If we use numerical calculus instead of analytical calculus, what we mean by that is we're doing effectively the rate of change step by step. So we're not using rules of calculus and we're getting an approximation. So for every 0.01 step in time, we get the difference in the height and we record that there. And we get a numerical rate of change. And again, this is an approximation, but what we're looking for is down here. We want to know when the rate of change becomes 0. We can see there we've got a positive rate of change all the way up to here, and then it goes negative. So we know between 0.71 and 0.72, then we must reach maximum height. And in that column there, that's the approximation from numerical calculus. In this column here, we've developed a formula for the rate of change from the original one. And if we execute that for every single value of time, again, if we go down here, we're looking for rate of change of 0. So we get again here, we get between 0.71 time and 0.72, the rate of change must be 0. So, and we get that time there if we actually solve the calculus rate of change. We get the exact time as 0.71356. If we plug that into the original formula, then we get the maximum height of 7.995. Now, what we can do is if our original equations are correct, we can insert a graph, recommended charts. Let's choose that one there, and let's see what it looks like. So what we've got here is we've obviously got a curved view of the height against time. So we start at height 3 above the ground at time 0, and we can see graphically that the height goes up to 7.99, and we can read off the values just by a visual check on the graph. And then that's where, at that point there, we get maximum height where the rate of change is positive here, and then the rate of change is negative here if we look at the tangent to the curve. So at some point up here, it has to be 0. And we can read that off the graph as well. And we can also read the graph off here when height is 0 for the time. For the height is 0, it's saying there 1.62. The shape of that curve is a parabola because it's a quadratic formula. We're describing the height of the ball, the vertical height of the ball against time, and we're not including any air friction in. So we've got quadratic equation here, and we form a parabola-shaped graph. Thank you for watching.